Welcome to Empowered Learning. This is the second video in the video series on Introduction to Hyperbolic Functions. So in this video, we will start by doing examples of taking the derivative as well as finding the integral of certain hyperbolic functions. So with our first example here, we are asked to find the derivative of this function 5 sinh of x divided by 4. And so we take the derivative. We know that since this is a composition function, we are going to have to take the derivative of the outside function first times the derivative of the inside function. So we know that we can ignore the 5. The derivative of sinh of blah is just cosh of blah. And then we multiply that times the derivative of the inside function with respect to x. And of course, there's an understood 1/4 here. So all that we're doing is taking the derivative of x with respect to x. So all of that just ends up being 1/4. So our final answer here is just 5/4 cosh of x divided by 4. And that will be the answer to this particular question. So for our next example, we're going to do the same thing, take the derivative. We see we have a 2-term function now. And of course, here we have secant hyperbolic squared. So we're going to look at this way. I'm just going to rewrite it for clarity here. I'll look at it like this. And let's make those grouping symbols a little bit different. So I'll take the derivative of that, and we'll do the same thing with the tangent hyperbolic. And so I'm writing it this way so that you know that, yes, we will be using the chain rule for this. So the derivative of the first term will just be the derivative of blah squared, which would just be 2 times blah. And of course, I'm saying blah to cover secant hyperbolic, times, now we need to do the derivative of secant hyperbolic, and we'll do that in the next step. Of course, here we also have derivative of blah squared is 2 times blah again, and then that's times the derivative of tangent hyperbolic with respect to x. So now we go here and we need to take the derivative of secant hyperbolic, which is just going to be a minus secant hyperbolic times tangent hyperbolic. So here this will be 2 secant hyperbolic here times a minus secant hyperbolic times tangent hyperbolic. And this will be 2 times tangent hyperbolic here. And the derivative of tangent hyperbolic will be secant squared hyperbolic. So now from here we will try to combine what we can here to make this look nice. All right, so now that we have this looking a little bit nicer, we see here that we have a secant hyperbolic squared in both terms, tangent hyperbolic in both terms, and a 2 in both terms. But 1 is minus, 1 is plus. So we see that essentially these are opposite terms of each other. So because of that, our answer is going to be 0 because these 2 terms will cancel each other out. So for our next example, we see that we have a composite function where the inside function is tangent hyperbolic. The outside function is going to be sine inverse. So notice that we're mixing a inverse trig function with a hyperbolic function. So we have to be careful on making sure that we don't get the derivatives mixed up there. So first thing that we want to note is that if we take the derivative of sine inverse of x, which is the same as arc sine, we know that's just going to be 1 divided by square root of 1 minus x squared here. Okay, so we know that. We also know that if I take the derivative of tangent hyperbolic, then that is going to be secant hyperbolic squared. Okay, so we're going to use those two facts there to help us out. So therefore, the derivative of our function y with respect to x, since this is a composition function, we're going to take the derivative of sine inverse of blah first. So that would just be 1 divided by square root of 1 minus, and in place of blah, we're going to put tangent hyperbolic x, and that's going to be squared. And then that's going to be multiplied times the derivative of our inside function here, which we know is going to be secant hyperbolic squared. So now from this point, one of the things that we know, and I'm just going to rewrite this. Here, well, we recognize that 1 minus tangent hyperbolic squared is an identity. And so I'm going to kind of derive it here just so you can see that. So we know here that cosine hyperbolic squared of x minus sine hyperbolic squared of x is equal to 1. Okay. So here, if I was to take this and divide both sides by cos squared here, then what this would end up being is just 1 minus tangent hyperbolic squared, and that would be equal to secant hyperbolic squared. So we see that what we have here under the radical in the denominator, that's just another way of saying secant squared hyperbolic, or secant hyperbolic squared rather. So here what we're going to do is we'll just tie that together there. So therefore, the derivative of this function with respect to x is now just going to be 1 divided by square root of secant hyperbolic squared, and that is just going to be absolute value of secant hyperbolic. And I've been forgetting to write this secant hyperbolic squared here, so I need to go ahead and write that in. So I'll write that in on top here. So that'll just be secant hyperbolic squared here, secant hyperbolic squared here. Now at this point, we need to decide whether this is going to be a minus secant hyperbolic or a positive secant hyperbolic in the denominator here. And to do that, we need to refer back to what the graph looks like. And I'm going to go ahead and stop the video and switch to that now so that we can decide on what we need to write here in the denominator. So referring back to the graph of secant hyperbolic here, we see that the range of this function is in between 0 and 1. So it is always above the x-axis. So that means none of its y values will be negative. So we can look at absolute value of secant hyperbolic as just regular secant hyperbolic. So from that, we know that the denominator is going to be positive. All right, and so from here, we could just basically say that the denominator is just going to be secant hyperbolic. And of course, once we simplify that fraction there, we would just have secant hyperbolic of x as our final answer. So for this next example, I've already have it worked out here, but we see again that we're dealing with a composition function. And so now we're going to have to take the derivative of the outside function, which is natural log of blah. And so the derivative of natural log of blah is just 1 over blah, which is what you see here. And then after that, we have to take the derivative of the inside function, which is going to be tangent hyperbolic of 1/2 x. And of course, tangent hyperbolic of 1/2 x in and of itself is a composition function as well. So we have to take the derivative of the outside function, tangent hyperbolic, which is secant squared hyperbolic of blah, times the derivative of the inside function, or the derivative of blah with respect to x. And of course, for here, the derivative of 1/2 x is just 1/2. So once we put that all together, we see that we just have sec squared of x divided by 2 over, and that should be tangent hyperbolic. Yeah, I need to put an h there. It should be tangent hyperbolic of x divided by 2. And so then from there, it's just looking at the fact that secant hyperbolic is the reciprocal of cosine hyperbolic, and tangent hyperbolic is the quotient of sine hyperbolic and cosine hyperbolic. You can see how I switch all that in. And then of course I do the arithmetic manipulation here. And eventually what I get to is I have this cosh of x divided by 2 times sinh of x divided by 2 times 2 in the denominator and 1 in the numerator. And we know this is going to be an identity, and that's very similar to the identity of sine of 2x, but since we're dealing with hyperbolic functions, it's going to be sine hyperbolic of 2x. And so the x, or the argument, is just going to be x divided by 2. So that's why we have that there. And of course, 2 times x divided by 2 is just x. And the reciprocal of sinh is going to be cosecant hyperbolic here. So that will be our final answer for example C. Now we'll move on and do example D. So for example D, we see here that our first term is the product of two functions. So we'll need to use the product rule. So we'll start off by taking the derivative of the first function times the second plus first times derivative of the second function. And then for the second term, this is a composition function here. So I'll just go ahead and take the derivative of that because it'll be relatively easy to do now. So I have 1/2. The derivative of cosh is going to be sinh. And then of course, since 2x is a function in and of itself, we would have to take the derivative of the inside function, which is 2x. So coming back here, we know that the derivative of x with respect to x is just 1. And so 1 times sinh of 2x is just going to be sinh of 2x plus x times the derivative of sinh of 2x. We're going to use the chain rule again. It's going to be cosh of 2x times the derivative of 2x with respect to x. And then for this last term here, we know that the derivative of 2x is just 2. So we can say the same thing is right there. And so from that, oops, wrong color there. So from that, we know that we have sinh of 2x plus 2x times cosh of 2x minus 1/2 of sinh 2x. And then finally from there, we see here that we have 1 sinh of 2x minus 1/2 of sinh of 2x. And that would be right, but I forgot to bring my 2 down here. So we'll bring down the 2. And so now we know that this 2 and this 2 will actually just be 1. So we'll have both of those terms there cancel to 0. And all we have left is our 2x times cosh of 2x. And let's fix that. And that'll be our answer for that question. So next we're going to switch gears here and start to do some basic integration. We'll start off evaluating indefinite integrals, which is just us really finding the most general antiderivative. And so for this first example here, if you think about whenever we take the antiderivative of sine of 2x dx, if you work with this enough, you'll know that the antiderivative of sine is going to be a minus cosine of 2x. But because of the fact that we would have to use substitution, we would end up with a 2 down in the denominator there. And that mainly comes from the fact of using the substitution rule. And so I'll just go ahead and write that out here. So if u was 2x, then that means du is going to be 2 dx. And then of course du over 2 would just be dx. So we could rewrite our integral here as just sine integral of sine u times 1/2 du. Okay, and I'll just write the du up there. So that's where that 2 in the denominator comes from. Our problem is going to follow suit. It's going to be the same thing. So here we know that the antiderivative of sinh is cosh. And of course, just like how we would here, doing this u substitution is going to give us a 2 in the denominator here. So our answer is just simply cosh of 2x divided by 2, all that plus some integration constant. So for our example B, you see that this is already worked out. And again, the main thing here is that, number one, we understand that whenever we take the antiderivative of secant hyperbolic squared, that's just going to end up being tangent hyperbolic. But since we have an inside function, x minus 1/2, we'll have to use substitution here. And it turns out that this ends up being relatively easy since the derivative of x minus 1/2 is just 1. So whenever we do the substitution, du is equal to dx. And thus, here we can just say that the antiderivative of secant hyperbolic squared of u is just going to be tangent hyperbolic. And then we just substitute in the x minus 1/2 for u. And then, of course, add our integration constant on the end there. So for this example, one of the things that we want to note here is that this example is going to follow the example much like if we were taking the antiderivative of tangent. And if you remember here, the antiderivative of tangent would actually end up being negative natural log of cosine of x plus c. Or if we were to take the understood -1 and put it in the exponent, it would be positive natural log of secant x plus c. Okay, and all that comes from basically rewriting tangent as sine over cosine and doing the substitution rule. Now, I'm saying all that to say here is because that is pretty much what we would have to do here as well. But because of the fact that we have both this tangent hyperbolic here and this x divided by 7. Just this one time, I'm going to do it the long way, just so that it's clear on how we get to our final answer. So I'm going to erase what I have over here and go ahead and do this problem. All right, so first thing that we want to do is we want to note here that tangent hyperbolic of x divided by 7 is just going to be sine hyperbolic of x divided by 7 over cosine hyperbolic of x divided by 7. And we're going to say let u equal cosine hyperbolic of this. And so that's going to imply that the derivative of u with respect to x is just going to be sinh hyperbolic of x divided by 7 times a derivative of the inside function would be 1/7. And so from that, here we would want to get, since we're going to be rewriting this in this way, we want to solve for sinh of x divided by 7 dx. So that would mean that 7 du here is going to be sinh of x divided by 7 dx. We'll fix that. All right, so now that we have that, I can replace what I have here with just 7 du. And I can come here and replace cosh of x divided by 7. I'll replace all of that with just u. And so now if I take the antiderivative of that, of course I ignore the 7, and the antiderivative of the understood 1 over u is just going to be natural log of u plus integration constant. And here we know that our u was just cosh of x divided by 7. And so that ends up being our answer for this question. And let's make that look a little better here. Okay, so for our next example, instead of me kind of taking the shortcut and saying here that the antiderivative of cotangent hyperbolic is just going to be natural log of sine hyperbolic, I'm actually going to do this the long way by doing substitution, just in case you run into problems like this and you don't necessarily remember all those antiderivatives. You'll still have a way to do them. So here, the one thing that we should remember with these problems here is that cotangent hyperbolic is just going to be cosine hyperbolic over sine hyperbolic. Okay, so here I'm going to write it like that: cosine hyperbolic of x over sine hyperbolic of x dx. And so here what we will do is we'll let u equal sine hyperbolic of x. Then from there we know that du is just going to be cosine hyperbolic times dx. And so because of that, we're going to have all of this just replaced with du. We're going to have this replaced with u. And so now the last thing that we want to do here to make life easy for ourselves is to go ahead and rewrite our limits of integration in terms of u instead of being in terms of x. So I'm going to say here also, we know that u of natural log of 4 is going to be sinh of natural log of 4. And if you remember, sinh or sine hyperbolic, that's just going to be, and I'll write it up here, that's just going to be e raised to the x minus e raised to the minus x divided by 2. So everywhere where we see x, we're going to put a natural log of 4 in its place. So we're going to have e raised to the natural log of 4 minus e raised to the minus natural log of 4, all that over 2, which is the same as saying e raised to the natural log of 4 minus e raised to the natural log of 1/4, because we put this understood -1 here in the exponent for the 4. That'll be 4 raised to the -1, which is 1/4, all that over 2. And so now we know via our exponential and logarithm properties that e raised to the natural log of 4 is just 4, and e raised to the natural log of 1/4 is just 1/4. And all that divided by 2. And so now we just simplify here. So this 4 can be rewritten as 16 over 4. And our numerator ends up being 15 over 4. And that will end up just being 15 over 8. Okay. So that would be our first, our upper limit of integration here. So now we're going to work on the next one. Pen has some delay here, so we'll just start here. So furthermore, we'll have u of natural log of 2. So this is going to look very much the same way as it's going to be for natural log of 4. So here we'll have e raised to the natural log of 2 minus e raised to the natural log of 1/2, all that over 2. So that's going to be the same, which should just be 2 minus 1/2, all that divided by 2. So 2 minus 1/2 gives us 3/2, and we halve the 3/2, and that'll give us 3/4. So once we have that, then what we can do is go ahead and finish up. So I'm going to scroll down here. So now what this means, and I'm going to switch colors here. So what we now have is that what we started off with is now just going to be the integral, and on the lower limit it's going to be 3/4, on the upper limit 15 over 8, and we just have du over u. And of course the antiderivative of du over u is just going to be natural log of absolute value of u. And we evaluate that from 3/4 to 15 over 8. So this would be, since both of these numbers are positive, I'm going to drop the absolute value sign. This would be minus. And of course, using our logarithm properties, we can divide 15 over 8 by 3 over 4, which is going to be the same as 15 over 8 times 4 over 3. And so here we know that 4 divided by 8 is just 1/2. And we know 15 divided by 3 is just 5. And so our final answer there is just going to be natural log of 5/2. So for our next example, we have, again, cosh of natural log of t, all that divided by t. And of course, we are trying to evaluate that definite integral from t is equal to 1 to t is equal to 2. What should jump out at us right now is that, of course, if we let natural log of t be our inside function and use that for u substitution, then the derivative of natural log of t is just going to be 1 over t dt. So we have a way of covering that, and thus we can rewrite this integral in terms of u instead of having it in terms of t here. So let's do like this. Let u equal natural log of t, which means that du is going to be 1 over t dt. Okay. And so now that we have that, let's also go ahead and figure out what u of 1 and u of 2 is going to be. So we're going to say also u of 1, which is going to be natural log of 1, it's going to be 0. And u of 2, which is going to be natural log of 2. So therefore, this integral that starts out looking like this will now end up looking like this. Well, the integral, instead of 1 and 2, now we have 0 and natural log of 2. And we have cosh of u, and in place of the understood 1 divided by t dt, we're just going to have du in its place. Okay. So again, just to be clear here, we have this 1 divided by t dt. All of that is what our du is. And of course, this natural log of t here is just what u is. And of course, from there, we know that the antiderivative of cosh u is just going to be sinh u. And we evaluate that from 0 to natural log of 2. And so now what we can do is let's go ahead and evaluate this. We'll put it in this form here. And one thing we'll see is that sinh of 0 should be 0, but I'm just going to put everything in exponential form so that you can actually see that. So here, if we put sinh of natural log of 2 in exponential form, it's just going to be e raised to the natural log of 2 minus e raised to the negative natural log of 2 all over 2 minus e raised to the 0 minus e raised to the negative 0 all over 2. And that goes like that. And of course, e raised to the 0 is 1. So when we see this, this is just 1 minus 1, which ends up being 0 for everything. So that's how that ends up being that. For that first term there, remember this is going to be e raised to the natural log of 2 minus e raised to the natural log of 1/2, all that over 2. So this looks familiar. We've already done this, so let's go ahead and figure this out. And we know that this will just end up being 3/4 once everything is done. So for this next example, I have worked this out as if I do not know what the integrand actually is. But I do want to go ahead and say before we start here that this particular integrand if we go back and look, that is actually what tangent hyperbolic of x actually is, okay? But even if you did not remember that, you could still work out this problem, work out this indefinite integral by not using that. And that's part of the reason why I wanted to show this example here. So my point in all of this is that if we recognize that this integrand here is just tangent hyperbolic of x, then of course if I was to take the most general antiderivative of it, then I would automatically know here, if we remember our antiderivatives here, that this would be natural log of absolute value of cosh of x plus c, okay? And so you see that's what we end up with for our final answer. But again, if we don't remember this, then this kind of shows you how we can still back our way into that answer. So here, if we look at the denominator and we allow that to be our, allow u to be that for our u substitution, then if we took the derivative of e to the x plus e to the minus x, that's just going to be e to the x minus e to the negative x. And we see once we move the dx to both sides, that is exactly what our numerator is, e to the x minus e to the negative x, all that multiplied by dx. So we could simply just replace our integrand that we have here with the top part being du, bottom just being u. And so now we know that the antiderivative of 1 divided by u is just going to be natural log of absolute value of u. And so if we substitute back in what u is, which is e raised to the x plus e raised to the minus x, we have this expression here, and that could be our answer. However, we note that cosh of x is actually e to the x plus e to the minus x divided by 2, which means that I can multiply both sides by 2 and get that 2 times cosh is going to be e to the x plus e to the minus x. And that's essentially what we have inside the absolute value signs. So here we could rewrite this to where basically what you end up with is just natural log of 2 times cosh, okay? And so now from here, if we were to separate well, let's say since we know that this is a and this is b, so a times b here, we know from our logarithm properties we could rewrite this as natural log of a plus natural log of b. And so from there, of course, natural log of 2 is just some constant, and we can combine this constant with this constant to come up with a new constant. And if we have that, then we see that we just have a natural log of absolute value of cosh of x. And so this could be our final answer here. What I probably should have done, but I didn't write it here, is just go ahead and drop the absolute value signs. And I can do that here because the graph of cosh, if you remember, it is it's a sum of 2 exponential functions, one exponentially increasing, one exponentially decreasing, but both of them are always above the x-axis. So that means that the y values for cosh of x will never be negative. So I don't have to worry about having the absolute value sign there because of that. So this would be our most simple final answer. Okay, so for our final example in this particular video, we are going to take the most general antiderivative of square root of cosh x minus 1. And so the approach that I'm going to take here is, because we have a square root of something that could possibly turn into an identity for us, but we have to be able to get inside of the under the radical to be able to do it legally, I am going to use what's called the conjugate radical technique to help me to be able to do this. Well, I'm going to use a variation of a theme of that particular technique. So essentially what I'm going to do is this. I'm going to look at this function here as being that over 1. And what I'm going to do is rewrite what I have here by multiplying both the numerator and denominator by square root of the conjugate of what the radicand is. Okay. So the conjugate of cosh x minus 1 is just cosh x plus 1. And so I'm doing this because, of course, whenever I multiply square root of something times square root of something else, one thing that I know is that I can now legally multiply the two radicands together. And so if I multiply cosh of x minus 1 times cosh of x plus 1, I know that's just going to be cosh squared x minus 1. And of course, square root of that all over this. Okay. So now, if we remember, we know that cosh squared minus sinh squared is equal to 1. So if I was to rearrange this, I know that cosh squared minus 1 will be equal to sinh squared. So that means here my numerator is just going to be square root of sinh squared of x, not u. So let's switch that. And then here the denominator will still be the same. So now at this point, we know that the numerator here, square root of sinh squared, will actually be absolute value of sinh x. Make those absolute value signs a little bit thicker here. All that divided by square root of cosh of x plus 1. And so here, because of the fact that we have no limits of integration here on our integral sign, what we are going to need to do here is just write this sine hyperbolic of x, the absolute value of that is just plus or minus for now, because sine hyperbolic could be positive or it could be negative, depending upon the values of x that we have here. We know that in general, absolute value of that is going to prevent the whole entire expression from the numerator from being negative. But we know that when x is negative for sinh, the result is going to be negative. And to kind of show you that, we can go back and look at the graph here. So if you look here, we see that, let me turn on the pen there, that for sinh x, for values of x that are less than 0, our graph is below the x-axis. So we do have to account for that, okay? All right, so back to our problem here. We see that our denominator will still stay the same. And so we're just going to carry that plus or minus on through to the end of this problem, and then we'll deal with the x values for where the result needs to be positive or negative at the very end. Okay. All right, so now that we have this, we know that the integral of square root of cosh of x plus 1 dx. Okay. We're going to rewrite this as plus or minus integral of sine hyperbolic of x over square root of cosh of x plus 1. and all this times dx. So now at this point, we can go ahead and use substitution. So we're going to say here, let u equal cosh of x plus 1. And so if we do that, then that means that du is going to be sinh of x dx. Okay, so we have a way of replacing the numerator here. And so for our denominator, that's just going to be square root of u. So I'll go ahead and write this in now. So all of this will just be du, and what's under the radical here, trying to do that again here. Get the 1 included there. All that is just going to be u. So because of that, what we're going to end up with here, and I'm just going to kind of take this equal sign and go like this with it. All right, so we'll see here that at this point, this will be plus or minus, and this will be du over square root of u, which will be plus or minus u raised to the negative 1/2 du. And then we'll just take the antiderivative of that, which will be u raised to the negative 1/2 plus 1, and divided by the same, plus constant. And we know minus 1/2 plus 2 over 2 is just going to be 1 over 2, and the reciprocal of 1 over 2 is 2. And so we see that we have, and I need to go ahead and write this plus or minus in there. So we don't want to forget that. All right, so pen, please work. Thank you. So we got that, and then of course we got the plus or minus here. And thus this will be plus or minus 2 square root of, and of course our u is just going to be cosh of x plus 1. And all that's going to be plus constant c there. And so now to finish up, we're at a point now to where we have an answer, but we need to know when is this particular result going to be positive and when is it going to be negative. And so that's what we're going to decipher now. So we're going to say that the most general antiderivative of this function here, we have a minus in there like that. We're going to make this piecewise, and so this will be a positive 2 cosh of x plus 1 square root of all of that plus c, and this will happen when x is greater than or equal to 0, and it will be negative whenever x is less than 0, or whenever x is negative. And again, that goes along with the graph of what sinh was trying to tell us. And so being that what we were considering here, which is sinh divided by square root of cosh plus something, we knew that we were going to have some negative values at some point. And so this is your actual answer. And of course, depending upon the domain that you use that most general antiderivative of that function for, that will determine what version you would want to pick. All right, so we've done a lot of examples of taking derivatives and integrals. So thank you for watching this video. The next video that I'm going to do with hyperbolic functions, we're going to go into rewriting inverse hyperbolic functions using their logarithmic equivalent way of being able to write them. After we do that, then of course we will do some more derivatives, but we'll do derivatives and integrals, but we'll do more so with inverse hyperbolic functions. So we'll kind of concentrate on those functions a little bit more as we end this. And so our part 3 video will be about those examples. I'll see you there.